All right, so hopefully you've become familiar with the three general types of acid-base reactions. And now what we're going to do is go over a few things that will hopefully help you with your homework. So here are four different species, and let's look at these and let's identify these as strong acids or weak acids and strong bases or weak bases. So here we have H2SO3, this is sulfuric acid. H2SO4, sulfuric acid is strong, so this one right here is weak. All right, here we have ammonia, and you just need to memorize that ammonia is a weak base. So this is a weak base. I forgot to put acid over here. Strontium hydroxide. Strontium is in group 2. It's one of the heavier group 2 metals. This is a strong base. And then we have hydrochloric acid, and that is a strong acid. Now, when these react, all right, what is going to be the reacting species? Well, for a weak base, because it's a weak base, it does not ionize at all. So when ammonia reacts, it is reacting as NH3. Same thing with a weak acid. When sulfuric acid reacts, this molecule stays as one of the reactants. But remember, in a net ionic equation, when you have a strong base, the strontium is going to end up being a spectator ion. So the species that is reacting for a strong base is hydroxide ions. For hydrochloric acid, the chloride is going to be a spectator ion when this ionizes, and so what reacts is the hydrogen ion. Excuse me. So really, for weak acids and for weak bases, their molecules exist in the chemical reaction. For strong bases and for strong acids, they're going to exist as either the hydrogen ions or the hydroxide ions in these problems. That's what's going to be reacting. So here's an example of a problem where you need to write a balanced net ionic equation. And you're going to have diethylamine with sulfuric acid. Now sulfuric acid is H2SO4, and look, we know that sulfuric acid is a strong acid. Now, diethylamine has a formula of C2H5. That's the ethyl, and there's two of those, and H3. Now, this doesn't look like calcium hydroxide. It doesn't look like strontium hydroxide, sodium hydroxide, but you're going to have to start recognizing that when you have this NH3 here, this is going to be a base because this is going to be able to accept a hydrogen ion. The other thing is, you know, this is the acid, and since we're doing acid-base reactions, this must be the base, and this is going to be a weak base. So we have a strong acid plus a weak base, and the general form for that reaction, right, is we have your base plus the hydrogen ion from the strong base to give you the base with the hydrogen ion added to it. So we're going to have dimethylamine plus the sulfuric acid isn't going to be in this net ionic equation as H2SO4. It's going to be in this as the hydrogen ion, and I'm going to draw my arrow down in this direction so I have some room. So we're going to get C2H52N, and this hydrogen's going to add right there. So we're going to get NH4 plus. All right, so that's our product between this weak base plus this strong acid. So here's another example where we need to write a net ionic equation. So we have aqueous hydrogen cyanide. Oops, look at that. Let me fix this, sorry. Alright, so HCN, and then we have sodium hydroxide. Sodium hydroxide is NaOH. So sodium hydroxide, we should realize, is a strong base. This looks like an acid. It's not one on our strong acid list. So this is a weak acid. And you should sort of be getting the idea right now that if it's a weak acid, it's going to exist as this molecule in the net ionic equation. So we're going to we have our basic reaction, which for a weak acid is HA plus the strong base is represented by hydroxide, and that's going to react. The hydrogen is going to go with the hydroxide, and we're going to get A negative from our acid plus H plus OH negative is water. So for a weak acid, strong base, so here's our hydrogen cyanide acid plus hydroxide ions, and this is going to produce cyanide ions plus water. Probably not something that you want to drink, but here is our net ionic equation. Alright, in the next problem here, we're going to put what we've learned about writing acid-base reactions to a real problem. So what volume of 0.285 molar strontium hydroxide is required to neutralize 25 milliliters of hydrofluoric acid? So we have strontium hydroxide reacting with hydrofluoric acid. So we have a strong acid and we have a strong base. So basically our net ionic equation is going to look like this. And so look, we know we have, well, I think I've left something out of this problem. Give me 1 second here to fix this. So what I left out is that the hydrofluoric acid is 0.275 molar, because we have to have that, otherwise we can't solve the equation. Alright, so look, we have the volume of our hydrofluoric acid, we have the molarity, so we can figure out moles. Strange noises coming from upstairs in my house. I'm not sure what's going on, but it sounded like an accordion. So if I'm not at school tomorrow, I don't know what's happened. Oh yeah. Alright, so molarity equals moles over liters. We want to find moles. So moles equals molarity times liters. So we're looking for the concentration of hydrogen ions produced by this hydrofluoric acid. So there's one hydrogen ion per hydrogen fluoride. So we have 0.275 molar times 25 milliliters divided by 1,000 is 0.02500 liters. And that is going to equal 0.00, what do we need? We need 3 sig figs, 688 molar hydrogen ions. Alright, now if we look at this, for every 1 mole of hydrogen ions, we get 1 mole of hydroxide ions. So for this, I don't even think you really need to show your work. So if we have 0.00688 molar hydrogen ions, we're going to get 0.00688 molar hydroxide ions. And what we want to figure out then is what was the volume of this that we need. Now, if you look at this, when strontium hydroxide dissociates, right, for every one strontium hydroxide, we're going to get one strontium ion plus 2 hydroxides. All right. So we have 0.00688. Oh, and this isn't molarity, right? This is moles, so I screwed that up. Sorry. So 0.00688 moles of hydrogen, so we have 0.00688 moles of hydroxide. So 0.00688 moles of hydroxide, and then we know for every 2 moles of hydroxide, we have 1 mole of strontium hydroxide. So the moles of strontium hydroxide is going to be half of 0.00688. So we have 0.00344 moles of strontium hydroxide. And I'm running out of room here. I need to make some space. But let's see if I can squeeze this in. So this is how many moles we have in 0.285 molar. So what's going to be the concentration? So molarity equals moles over liters. So the molarity we know is 0.285. The moles is 0.00344 over liters. So sorry, this is getting kind of crowded. I'm running out of space. So look, so liters equals, multiply both sides by L, right? Those cancel out. So you're left with liters is 0.00344 divided by 0.285 equals, I'm going to do that here, 0.00344 divided by 0.285 equals, so this equals 0.0121 liters. So it's really 121 milliliters of strontium hydroxide solution. Alright, sorry, that came into a big mess. Now, the key thing that you have to do here, though, is once you have moles of hydroxide, you have to look at strontium hydroxide's formula, and you have to know that for every 2 moles of hydroxide, you only get 1 mole of strontium hydroxide. So you got to make sure you do that, or you're going to be off by, it's going to be double what it should be. So those are just some examples of acid-base problems. Hopefully this helps. You can ask me more questions in class if you need it.